This is the third video for Physics 12 for Chapter 1, and in this lesson we're going to take a look at relative motion. And if you're wondering, what is that all about? These were our boating questions and our airplane questions back from Physics 11. Not really a big emphasis on the actual boats and airplanes here, but really it's just a chance to practice adding and subtracting some vectors together. So imagine you're operating this boat, you're the captain, you're trying to get this barge maybe across to the other side, to the other shore, and you want to make sure that you anticipate the current. If you anticipate the current and tip your boat correctly, then yeah, you might end up at this location A up here. But if you don't anticipate the current and just point straight across, you might end up over at B. Again, not too worried about the whole boat plane thing because we did a lot of that in Physics 11. This is just a chance to practice working with vectors again. So here's the story. Imagine you've got one shore over here, there's the beach, and there's the other beach, and you're in this nice little yellow boat, and you're trying to get across this river. It's a huge river. It's like the Nile or something. It's 6,000 meters across. It's 6 kilometers across. I just made the numbers up to get the math to be nice, so maybe it's a bit artificial. Going to be a lot of vectors here, so sometimes people put these little subscripts on the vectors. So they might say the velocity of B compared to W, okay, the boat compared to the water, or getting all fancy, with respect to, with that WRT abbreviation. So let's say your boat slices through the water at 12 meters per second, and you're just going to aim north. So this is not going to be good if there's any current, and there's going to be current. This distance across there, 6,000 meters, and here comes the current. Let's say that the water, the W, is moving compared to the G, moving compared to the ground at 5 meters per second to the east. So this isn't going to go well for the boater if they just aim their boat straight across, right? They're going to get kind of carried diagonally. And so the equation, well, this is kind of generically true. If you take something that's a velocity of B compared to W and add on W compared to G, okay, so boat compared to the water, water compared to ground, then you get B compared to G, boat compared to ground. So let's add those two vectors together, the 12 and the 5. Now I'm kind of violating my advice from the other day when I said, try to draw the picture so that you end up with an angle that's compared to the east-west line, and this one's going to end up being compared to the north line. That's actually pretty common for boaters. They like to talk about, well, how many degrees am I being pushed off course by? So yeah, we'll tolerate it this time. So you run the numbers. Geez, it goes by pretty quick. It's that nice Pythagorean triple again. So Pythagoras offers us 13 meters per second for that resulting velocity, and then a quick inverse of tangent, and we see that the angle right here, okay, in this little pocket right there, is 23 degrees. So that's your angle that you get pushed off course by. Sometimes a boat captain might say, oh yeah, that's our downstream angle, right? How many degrees towards downstream are you being shoved? Great. So this thing is wrapped up pretty quick. Got our velocity of the boat compared to the ground. It's 13 meters per second, 23 degrees downstream, or getting more precise, 23 degrees, a little more dialed in, 23 degrees east of north. Okay. Let's see what else we can do with this question. We haven't used this 6,000 yet. Let's see how long it'll take to cross the river and how far downstream will be. Kind of just some simple little review questions from last year, but I'm just using them to talk about some sig figs here in the end. When you go to figure out how long it's going to take to cross the river, this 6,000 is pointing straight across the river, and our advice to you in Physics 11 was, well, find which velocity points straight across, and that's the 12. I'm going to change that advice later on as we do one question deeper in the course. I'm going to suggest to you that you want to look at this blue one and ask yourself how much of the blue one points straight across, which of course is 12. But if the pilot was to aim the 12 at a funny angle and then the 5 makes it worse, we might have to modify our thinking. But for now, this will be great. So just like Physics 11, 6,000 meters to go, 12 meters per second across, and we end up with this number 500 seconds. Now, I just wanted to cook up this quick little example to talk about this answer. So, the deal with sig figs. Significant figures are important, or significant digits, whatever you'd like to call them. They're important. Scientists communicate with each other in very careful ways where we want to convey how much confidence we have in a number. And it is a very good skill to be able to look at a question, see how confident you are in the numbers in the question, and then respond with an answer and say, this is how confident I am in the answer. And so I'll use sig figs to express that. So it's part of our whole communication thing, you know, with critically thinking about numbers. We use that as one part of our communication with each other. We spent a full chapter in Physics 11 dialing in exactly how to get that right based on the question. And we then, after that chapter, relaxed a little bit, and that's still true now for Physics 12, to the point where we say, hey, we respect the fact that scientists use sig figs to communicate confidence, and so we don't want to tell people that we're overconfident in this answer, so we don't want to write down 12 sig figs. So the rule for Penn High is 2 or 3 sig figs, your choice. And by doing that, you're making that commitment to saying, yes, I understand that this is a method that we use to convey confidence. This number here, how many sig figs does it have? This one's really open to debate. When you've got a whole number with no decimal portion and it ends in zeros, there are many people in the world who would say it's only got 1 sig fig. But there are others who would say, in this situation, if you write zeros after a number, you meant them, and this is 3. So I'm open-minded. I'm going to look at that and say, I don't know, maybe you wanted 1 sig fig or maybe you wanted 3. Well, 3 makes me happy. It's an acceptable way for a student to leave an answer. So if you leave an answer like that on a test, I'm going to say, oh, I bet you wanted all 3 of those to be significant, because that's one of our acceptable ways to leave an answer, and I would mark it right. Then you go and you do the very next question, the distance downstream that you missed by. We know you're in the water for 500 seconds, so you multiply by your downstream velocity, your sideways velocity of 5, and you get this number, 2,500. Now, I would look at that and go, oh, I don't know. Many people would say only 2 sig figs. But there are others who say, hey, the zeros are after a number, you wrote them, you meant them. Maybe the student wanted 4. And I would ask myself, well, is either of those okay? Is either 2 or 4 okay, according to our Penticton secondary rules? And the answer is sure, 2 is okay. So I would look at that number and say, oh, you probably wanted 2, and I'd mark it right. Just like I'd look up this one and go, oh, no, you probably wanted 3, and I'd mark it right. So I will do whatever I can to actually give you the benefit of the doubt on numbers that look like that. And it's only those whole numbers that end in zeros that are a problem. Okay, let's take a look at airplanes. For airplanes, we've got actually, let's just put all this up here. You've got 3 different velocities we like to talk about. The velocity of the plane compared to the air, okay, or with respect to the air, we'll call that VPA. And then the velocity of the air compared to the ground. It's just like boaters, except we have the air instead of the water. And then the plane compared to the ground when we put it all together. So here's the equation. It is exactly like the boating one. If you take a V of P compared to A and add on a V of A compared to G, it's like the little A in the middle drops out, and you'll have the velocity of the plane compared to the ground. Now in Physics 11, we actually used airplanes as a way to practice working with triangles that did not have right angles. So perfect. Let's do that again. We'll kind of practice that a little bit. Pilots have very special names for these vectors. Remember, each vector has 2 parts. It has size and direction. The wind is pretty obvious. The speed the wind goes is called wind speed, and the direction the wind goes is called wind direction. For physics, we're going to talk about the direction the wind is going. Meteorologists talk about where it comes from, right? But we're going to talk about which way it's going. For the plane going through the air, the speed that the plane slices through the air is actually called the airspeed. It's kind of a little bit mislabeled, right? Is that how fast the air goes? No, it's how fast we're going compared to the air. And the direction the airplane is physically pointing is called the heading. So think of that as being like the pilot's head as they look straight out the window. That's the heading. The ground speed is not how fast the ground is going, but it's how fast you're going compared to the ground. And track is the direction you actually go. Okay, so if you wanted another quick way to think about how this works here, wrong spot here. The heading is which way you point, and then the track is which way do you go. All right, let's try a question out here. So let's say you've got this desire to fly 8 kilometers, or if you need it to be 8,000 meters. Your desire is to go 45 degrees north of east, and you've got maybe it's like a little ultralight or something. It has one speed. Doesn't even have a throttle, just has a switch. You turn it on and it goes 20 meters per second. And it's a windy day. We'll say the wind is 12 meters per second going to the east. A pilot would actually call that a west wind, but we'll talk about which way it's going. Okay, so to the east. So let's compare the dumb and the smart pilot, as we called them last year. The dumb pilot says, oh, okay, I'll have to take my 20 airspeed and add on the wind, add on the 12, and that's correct, in order to find out where they go. And if I add those two vectors together, I can figure out where this plane will actually go. Now, in a second, we're going to finish this lesson up with the smart pilot. The only thing that changes is where the 45 degrees goes to. In fact, I just copied and pasted the notes, but I changed the 45. So this, again, is where we point. And this vector here is where we go. And so you can see that we are not going to go 45. We're going to point 45. So this is a bad situation, right? What we affectionately called the dumb pilot last year. So if you had taken that arc and only gone up to the green line, then it would be the smart pilot. And it just changes your cosine and sine law work. But this is going to be our dumb pilot, and we're going to see if we can figure out how this whole picture comes together. I would take this 45 and maybe do a little, alternate interior, zigzag, Z-shaped angles, whatever you want to call it, and say, oops, sorry, got that backwards. Try this again. I would take that, so right in here, this is 45, and that makes 135 degrees on that side of the arc there. Okay, so just kind of zigzagging the 45 up. Now I'm ready to go. I have side, angle, side, and I'm ready to start this question with the cosine law. So it goes pretty fast. Just drop that all into your calculator for the cosine law. You get a very large answer, of course, but you get to take a square root, and we can see how big that v vector is going to be there, your actual ground speed. It looks like it's more than 20, but less than 32, because those two blue vectors are not exactly in line. And yeah, it's around 29.7. Yeah, grab a few extra digits if you're going to use that number again. Great. The next thing I want to figure out is this thing called the drift angle. Right? How much do you end up drifting off course? If I can find that drift angle, then I can figure out actually which way we're going to go. So I'm going to use some sine law to find out that drift angle. So the sine of theta divided by its opposite side, which would be the 12, and then my working pair, right? So I've got this working pair here where I know the 135 and I know the v, so that's good. And when I go through that, I get 17 degrees. Yeah, technically, you should be wondering, is this the ambiguous case? There's no way it would be the other one, which would actually be like 163 degrees or something. It can't be that. So yeah, it's definitely 17. So this little tiny angle in here, 17 degrees. And then if you want, you can tell people which way you'll actually go, right? It's going to be the 45 minus the 17. So you're actually going to track 28 degrees north of east in this story. And you are going to miss your destination, because your destination would have been along this 45 degree line, right? So your destination is out here, and you're not going to go there. So why don't we finish this day up by taking a look at the best way to do this, the smart pilot that actually gets there. So the smart pilot, you don't need to recopy the question. You've already got it, right? It's the exact same story. All that's the same. No need to recopy. Smart pilot, I pretty much just cut and pasted that. The change that I'm going to make is where the 45 degrees goes. I'm going to put it here because remember, the 20 is the way that you point the plane, and this green one is the way that it goes. Well, I desire to go 45 degrees, so I'm actually going to go and put that right there. That changes the way this story works, because now when I go and do that little Z-shaped angle thing, the 45 degrees goes up here, right? When I do that move. That'll change how we do the math. And now as we begin, we might want to do the sine law first with this drift angle and the 12 degrees. And then you've got this working pair with the 20 and the 45. So a little cross multiplying, 12 times the sine of 45 divided by 20, get that done, and then unsign it. And we see that that's 25 degrees. So if you really want to tell the pilot, hey, this is the way you're going to have to point the plane. Here's your heading. Then we need to add on 25 degrees there. We can add that to the 45 and say, hey, your heading needs to be 70 degrees, right? So all the way up from east. Got a 70-degree angle in there. Now you're actually going to make it there, so you could figure out how long it'll take, right? You could say, all right, unlike the dumb pilot who doesn't make it, I've got 8,000 meters to go, and I'm traveling at a certain ground speed. So why don't we go find that ground speed, and then we can find out how long it'll take. To get that ground speed, I'm going to have to go after this other angle in here. Remember, this was 25 degrees, and then 25, 45, that adds up to 70. So if I subtract that 70 from 180, this is 110 degrees up there. I'm going to need that in order to do the sine law for this, to find out what that velocity of the plane is compared to the ground, right? So yeah, again, I got 110 degrees up there. Okay, well the sine law falls apart pretty quick. Just do some cross multiplying to find that velocity. Ends up being around 27, 26.7, whatever you want to call it, meters per second. And then a quick little d equals vt backwards to find the time, and it's done. Want to go 8,000 meters, 8 kilometers, and it's going to take 300 seconds, so like 5 minutes, and then you'll be there. Not really worried too much about boats and planes, in Physics 12. I'm not going to have those kind of questions on the test. It's really just an issue of practicing this idea of adding vectors together and including vectors like this that are not at a right angle, and you have to use the sine law and the cosine law. And so that wraps up our third lesson.